Hi, Chris Good here. We're going to try a practice ANOVA problem, and this is one of the 3 problems we have from Linda Wolf at Webster University. Thanks very much to her. And let's just read it very briefly. Research study was conducted to examine the clinical efficacy of a new antidepressant. Depressed patients were randomly assigned to one of 3 groups, placebo, low dose, and moderate dose, and after 4 weeks of treatment, they complete the Beck Depression Inventory, and the higher the score, the more depressed the patient. We're looking for a decrease in depression scores. You go from placebo to a dose of the drug and compute the appropriate tests. Well, these are 3 groups of different people, so we need an independent groups analysis of variance, and we do the same steps that we do for every hypothesis testing statistic, and that's step 1 is state the null hypothesis. In the t-test, you have 2 population means you hypothesize about. This independent groups ANOVA, we have 3 in this case, and the null hypothesis is that this treatment has no effect, so it's as though these samples are coming from populations with identical means. So the mean for the placebo group is equal to the population mean for the low dose group, which is equal to the population mean for the moderate dose group. That's our null hypothesis. Step 2 is to look up that critical value for your statistic, in this case the F statistic. F is distributed on 2 different types of degrees of freedom, and so we need to find out what those are. Remember, the equation for F that we're going to end up using is the variance between groups, but we call it the mean squared between treatment groups, divided by the mean squared within, or the variance within treatment groups. Okay? And in the F table, I've got one on my iPad right here. It's weird we're using an iPhone to film an iPad. It tells you in the F table, here are the degrees of freedom in the numerator, that's the numerator of the F ratio, and these are the degrees of freedom in the denominator, that's the denominator of the F ratio. Well, if we use variance between treatments in the numerator, we need to use degrees of freedom between treatments in the numerator, and variance within treatments is in the denominator. We need within treatments degrees of freedom to look that up. So let's compute those. The degrees of freedom in the numerator, so between treatments, is simply the number of treatments that you have, or K, minus 1. We have 3 treatments, so 3 minus 1 is 2. The degrees of freedom within treatments, that's just summing up all of the degrees of freedom within each treatment group. So the degrees of freedom for these 5 scores is 5 minus 1 or 4. For these 5 scores, it's 5 minus 1 or 4. For these 5 scores, it's 5 minus 1 or 4. Altogether, 4 and 4 and 4 is 12. There's a faster way to do this. You take the total number of scores that you have, and you subtract 1 for each treatment group that you have, and that's the same thing as subtracting K. Okay? So the number of scores we have is 15, 3 times 5, minus the number of groups we have, which is 3, and look, we got the same answer, 12. Okay, now we can go to the F table and look up our critical value for 2 and 12 degrees of freedom, and that's how we write it. So for 2 and we'll scroll down 12 degrees of freedom, the critical value for F is 3.88. So that is the score to beat. By the way, here's a picture of the distribution of F. Even though it has a tail down here, all ANOVAs are, by definition, a one-tailed test. We're looking for greater variability between groups than within groups, and so we're only looking in this tail. There's only ever one tail in an F distribution. Okay, so step 3 is always compute your test statistic, right? And that's going to be the mean squared between treatments, or the variance between treatments, divided by the mean squared within treatments. Variance within treatments. Well, to get variance, you need sums of squares. So let's start with the sums of squares within treatments. We kind of have our work cut out for us because we don't even have the sums of squares for each group. And the sum of squares within treatments is just the sum of the sums of squares for each treatment. So we need the sum of squares for this group, and this one, and this one. Okay. The first thing I'm going to do is get the totals, right? The sum of all the scores in each group. So T for the first group, placebo group, is just the sum of all these scores. 38, 48, 39, 25, and 42. So that's 192. T for the second group is 22, 19, 8, 23, and 31, or 103. For the moderate dose group, it's 14, 26, 11, 18, and 5. And the T here for the third group is 74. That's going to come in handy when we do these sums of squares. Because the sum of squares for any distribution is equal to the sum of the squared scores minus the square of the sum of the scores divided by the number of scores. Let's go ahead and calculate the squared scores for each one. So 38 squared is 1444. 48 squared is 2304. 39 squared is 1521. 25 squared is 625. And 42 squared is 1764. For the low dose group, 22 squared is 484. 19 squared is 361. 8 squared is 64. 23 squared is 529. And 31 squared is 961. For the moderate dose group, 14 squared, 196. 26 squared, 676. 11 squared is 121. 18 squared is 324. And 5 squared is 25. Alright, now that we've done that, doing sums of squares for each group won't be so bad. So the sum of squares for the placebo group, right, is the sum of the squared scores, and I already have those, 1444 plus 2304 plus 1521 plus 625 plus 1764 minus the sum of the scores squared. I already summed the scores, that's 192, squared over the number of scores, which is 5. So that's 1444 plus 2304 plus 1521 plus 625 plus 1764. That's a total of 7658 minus 192 squared, which is 36,864. Don't forget to divide that by 5. That's 7658 minus 7372.8, right? Or 285.2. Okay, 285.2. That's the sum of squares for the placebo group. I'll write that down here. Sum of squares placebo is 285.2. Let's do the next group. Okay, so the sum of squares for the low dose is equal to the sum of the squared scores minus the square of the sum of the scores over the number of scores. That's 484 plus 361 plus 64 plus 529 plus 961 minus 103 squared. Where'd I get that? That's the total for the column over n, which is 5. 44, 361, 64, 529, and 961. 2399 minus 103 squared, which is 10,609. Don't forget, divide by 5. So that's 2399 minus 2121.8. Or 277.2. So the sum of squares for the low dose group is 277.2. Let's do the moderate dose. That's the sum of the squared scores minus the square of the sum over n. Or 196 plus 676 plus 121 plus 324 plus 25 minus 74 squared. Where did I get that 74? Right here. That's a column total of the scores, not the squared scores. Divided by 5, which is n. Alright, 196, 676, 121, 324, and 25 is 1342 minus 74 squared, which is 5476. Don't forget to divide by 5 or you'll get a negative number, and you cannot have negative sums of squares. That's 1342 minus 1095.2, or difference of 246.8. 246.8. Alright. Now, like I said, the sum of squares within treatment is the sum of those sums of squares for each treatment, or 285.2 plus 277.2 plus 246.8. 285.2, 277.2, and 246.8. That's 809.2. And that is our sum of squares within treatments. We need in the numerator, in the denominator, the mean squared within treatment, so the variance. And the variance is always sums of squares over degrees of freedom. And we're talking about within treatments variance, so we use within treatments sums of squares and degrees of freedom. So 809.2 over, what was our degrees of freedom within treatments? It was 12. So divide that by 12 and we'll get 67.43 with rounding. That's going to be the denominator in our F ratio. Now, what about sum of squares between treatments? This is a new formula. It's the sum of all the t-squares divided by n minus g squared divided by big N. And g is the sum of all of the scores in the whole study, which is the same thing as the sum of the column totals, right? So we already summed to get the column totals, and we'll just sum the column totals, 192 and 103 and 74, to get g. That's 369. Alright, well, what were our t-squares? Well, there was 192 squared over n for that group, which was 5, plus 103 squared over n, which was 5, plus 74 squared over n, which is 5, minus 369 squared over big N, which is the total number of scores in our group, which is 15. Not just a group, but the whole study. Alright. So, 192 squared is 36,864 divided by 5 is 7,372.8. 103 squared is 10,609, right? Divided by 5 is 2121.8. 74 squared, you know, we did this in all of these steps, right? To get sums of squares. is 5476 divided by 5 is 1095.2 minus 369 squared is 136161. Divide that by 15 and you get 9077.4. Let's add 7372.8, 2121.8, 1095.2. That's 10592.8 minus 9077.4. And we get 1515.2. I missed a digit here. Let's try that one more time. Alright, so let's do this adding one more time, because I think I made an error. 7372.8 plus 2121.8 plus 1095.2 is 10589.8. Sorry, minus 9077.4. So I get 1512.4 for sum of squares between treatments. Let's copy this over here. Sum of squares between treatments is 1512.4. But in our F ratio, right, we want sum of squares, we want the mean squares between treatments divided by the mean squares within treatments. Or variance. And variance is always sum of squares over degrees of freedom. Only this time it's between treatments. So that's 1512.4 over degrees of freedom between, which we already calculated. It's 2. So I get 756.2 for our mean squared between. And now we can plug that in to our observed F equation. Mean squared between treatments over mean squared within treatments. So 756.2 over 67.43. And we get our F as 11.21. Okay. 11.21 is our observed value for F. The critical value is 3.88. Step 4 is to make your decision. We're going to reject the null hypothesis and conclude, we would never write that in our sentence, but we conclude that drug treatment has a significant effect on Beck depression inventory score. And we'd report our F values like this. The F, you have to get both degrees of freedom. For 2 and 12 degrees of freedom is equal to 11.21. We know that the probability here is less than alpha, because we chose the light face type. The bold face type is for an alpha of 0.01. Okay. In the next video, I'll show you how to find out which one of these treatments produced scores that were significantly different than which other one of these treatments. We'll see you then.